But yeah, I'm happy to be here and to be able to talk about confidential containers, which is a multi-vendor open source project that I get to work with at Microsoft, along with folks from different cloud providers, GPU vendors, CPU vendors, etc. Yeah, few words about me. So I'm Magnus. I've been in the software industry for, I don't know, many years, and I had several roles like architect, engineering manager, and currently I'm a software engineer at Microsoft, doing systems engineering in the Azure Core Linux organization. So what I want to cover in the upcoming minutes is essentially this. So first I want to give like the rationale why confidential containers is actually something that you might want to care about. Then I want to introduce the key concepts and technologies that are kind of a requirement to understand how you can leverage this technology. And eventually I plan to do a demo, which unfortunately doesn't work because it's on the other laptop. So this is something that we have to cover in text, but I think we can do that. Yeah, so eventually all those presentations start with about confidential computing, confidential containers. They start with the same sales pitch. So it's more or less like you have like 3 pillars of encryption. 2 of those we are familiar with. That would be like data at rest. This is like if you have a requirement to store, for example, your database in an encrypted form on your cloud provider. Data in transit we already know very well. It's TLS that we try to apply everywhere, and it's very common and accepted as something that you should adopt pretty much everywhere. And eventually the third pillar that is always identified as kind of the missing part is data in use. So data in use means the data that is processed by the underlying compute. That means like in RAM, and that means in CPUs, in registers, in caches, etc. This is at the moment more or less transparent for cloud users. That's why the like canonical definition from the Confidential Computing Consortium is saying that confidential computing is protecting the data by performing all the computations in a specific environment that's hardware-based, attested, and we get to understand those terms, hopefully, in a few minutes, in a trusted execution environment. Briefly, why should we be concerned about data in use? So in essence, we are just in our daily computing, we are detached from the physical hardware very often. Like even if you run on-premise, or it often means like you rent a slot in a data center somewhere, so it's not like you really physically have the machine under your desk. And someone could inject or malicious code. Someone could get access to data that we don't want them to have. We have also like the requirement, if you want to process sensitive data, that there's strong privacy requirements. So I think the obvious thing today is LLM agents, for example, that cannot run completely locally, but maybe they also do some retrieval augmented generation, and they go to some web service, and you cannot do just inferencing locally. So, but it processes very sensitive data. An interesting use case additionally is multi-party computations. I think in Germany we are aware of this, that often we have like data pools that are very interesting individually, but even more interesting when you join them. Think of like insurances and clinics. but you cannot just join two tables because this would give either party too much information. But the insights that you could retrieve from those kind of data sets when you join them could be very interesting. So confidential computing enables this, that neither of those two parties can actually look into the environment that is confidential. And eventually also a security aspect, you can just reduce the fallout of a compromise. Yeah, so just because someone is an admin, it doesn't mean they have access to all the data. Yeah, a brief reminder, I think, just for if we look at the public cloud environment, the VM state is transparent to the host. This is just inherent to the architecture. We have a sort of isolation in there, but that's between tenants. Yeah? So the host, the public cloud provider, they are essentially like Uber admins, and they can access the state of the virtual machine. And like roughly we can describe the state as RAM, CPU registers, caches, but there's also more stuff that you wouldn't intuitively consider. Just as a quick detour, so I won't go into much detail here, but we can inspect the memory of a VM, like locally, start a VM with QEMU, then log in, set some secret that we don't even persist here, we just write in memory. Then we go into the management console of QEMU and just briefly dump the whole content, and eventually, if we look into this content, we get the secret that we just typed into the console, and even amusingly, even the typo I made. Yeah. So it's not 2034, but it's 2024, and this is a kind of context that a VM host gets from its guests. So we kind of can maybe understand why we would want to have confidential computing, and essentially the question is also, why do we want to have confidential containers? And I think this is more or less driven by the fact that this technology is not trivial to implement and deploy, so only big companies can actually afford to do this at the moment, to have like their bespoke way of setting those components up. And cloud native today really provides us with a kind of interface and platform for applications that are standardized. Yeah. So we know how the environment in many companies look like, and they're more or less something that you can hook into. And this is essentially the rationale of confidential containers. So that means confidential computing will become accessible and popular if it's easily integratable in your container ecosystem. And essentially there's also a side to it that says we have like a North Star or a target, and this means essentially we want to lift and shift applications. So this means like you take an existing container and you really add just one annotation to it, and then it's confidential. So this is more or less what the project aims for, and at the moment this is also the case. So you add a runtime class to your pod spec, and this runtime class will then facilitate in the background what you require for a confidential container. The key concepts for understanding confidentiality, I think, are trust, integrity, and attestation. And if you don't cover those, sometimes it gets a bit weird, because you tell them, yeah, it's just, you know, like this one line in your pod spec, and then everything is confidential, and then you show people like how this actually looks like in practice, and it looks like far more complex, and then you kind of have to walk back on your promise. But it's just inherent to confidentiality that those concepts have to be considered. Yeah, I mean, if you look at trust in cloud computing, I think there's like intuition to say like, of course, we trust no one. We control everything. And I think this intuition is not right. There's quite a lot of implicit trust that we have in our deployments, in our software that we operate in the cloud. So it's first like we have trust in our code. We have trust in our deployments. Yeah, so we trust that maybe no malicious actor injected some environment variable that might be harmful. We have trust in our operation teams. We have trust in the cloud service providers and in the CPU vendors and other hardware vendors. And essentially what confidential computing wants to achieve is just to shrink this trust boundary. So this is something that I also often get as a feedback, that like what is actually removed, or how is my stuff more trustworthy by relying on certain parts and not going all in. Because what we can only do, we can essentially just remove like the in-between layer. Yeah, so we still have to trust CPU vendors and the GPU vendors to execute our code. So, I mean, this sounds sometimes a bit simple, but essentially it means like the CPU is really something that you implicitly trust all the time. So if the CPU doesn't perform the opcode you instruct it to do, then compromise is very easy. Like you can just inject, I don't know, some not random part into a seed, and then your encryption doesn't work anymore. So this is really something that we at the moment trust, and that we also in the future probably will have to trust, but all the pieces in the middle are something that we can remove from the trust boundary. Yeah, and as I mentioned earlier, so who do we want to trust in this case? If we have an assumption that the whole compute environment by itself is not trustworthy, we have to put the trust in an entity that is not part of that environment. And this means we have to have something that is kind of excluded, isolated from the rest of the environment, and this is already like existing technology that's called the root of trust. We know this from HSM and TPM. So they are physically sealed from access, and I think there's a good quote to describe what they actually are. I found this very instructive, is that is essentially a piece of hardware, a chip on your computer that you don't get to run code on. So this is critical. If you don't get to run code on that chip, the attacker also cannot run code. The second pillar is integrity. So integrity essentially means, what is our machine running? Is a machine really running what we intended to deploy? Like, is it according to specs, or is there an admission controller that injected something completely different, maybe in our Kubernetes application? Has our environment been compromised? And to answer those questions, we have one way, or there's one common way to do this, and this is called measurements. So this means we assess the integrity of a system by measuring its components. Measuring in this sense means we take a cryptographic hash function, basically. So I think this concept is not very alien for many. Like, we know this maybe when we download binaries, there's a checksum, and we can verify. We downloaded this binary from this website, and we might also want to verify that it's actually genuine and it hasn't been tampered with. This concept can be extended, yeah, or there's a way to extend hashes on top of each other. So this way you can not only like have a single piece that you trust, but also like multiple items that are chained together. So essentially you take one hash, and then you calculate the hash of the existing hash and the next value. and the digest is then the resulting hash of both components. And if we look at, for example, Linux measured boot, in this way we can record a sequence of events that happened. Yeah? So the firmware, once we start the machine, measures the bootloader. The bootloader measures the kernel, and the kernel measures the init.rd, and the init.rd has some means to measure the rootfs. And only, like, we can put blocks in each part. We can say, like, the bootloader will only boot certain kernels, for example, or the kernel will only start a certain init.rd, etc. So, but we can also just say, okay, we have a chain of events that is recorded. Essentially like Merkle trees and Git blockchains, those are the concepts. They are deterministic and replayable. The practical example, I think Ubuntu introduced this recently, is like disk unlock with TPM. So as in the previous slides, TPM have an extend-only hash register. So they cannot just arbitrarily written into, they can only be extended, those TPMs. And essentially they have to record this chain of events that we saw before. And here the boot process is measured into those special registers. And the TPM will only unseal the decryption key for a rootfs if a certain configuration of PCRs is in the TPM. Like, only if those events happen, the root disk can be decrypted. And here a compromised system in this setup would not be able to boot, like if you install a rootkit or something. This kind of verification that you turn on your laptop and it suddenly doesn't start anymore, it's not very, like, it works for this use case and it's a good threshold, but if you want to deploy this on a bigger scheme, it gets a bit impractical because you cannot essentially debug a machine that won't start. And you want to understand why the machine is not booting. And an iteration on this is remote attestation. That means a verification of this boot chain, for example, is put into an external system that we also trust. So it could be a box under our desk, it could be in a different account, it could be a different cloud provider, but it's a remote party, a relying party that we trust. And the root of trust hardware will continue to gather the measurements, but it will hand them over as a signed quote to the external verifier. And the verifier decides then, by looking at cryptographic signatures, whether this actually originated from a genuine TPM. Yeah? So the keys are really sealed in hardware. You cannot really physically easily extract the keys from them, and the user has no access to it. So only this hardware is able to sign the evidence that the verifier is able to give a state yes or no, or statement yes or no to. So this is a brief flow for the remote attestation, how this would look like. So we have the attester, this would be our VM or confidential VM, for example. It collects its evidence, sends it to the verifier. The verifier asserts it has been signed by an authentic hardware root of trust, and the measurements match the expected values. Then we get a token back, and this token we can hand to another key server that understands those tokens and can provide us with a secret we need for our computation. And essentially that's confidentiality. So confidentiality is really just integrity plus privacy. And confidential computing is just a technology in the CPU that is an iteration on those root of trust technologies that provides privacy guarantees. So it's very complex from the implementation side. From the user side, it's not very, very special or very different from the concepts that we had before. Here's like a short chart, like how this looks like. There's a secure processor. So this is the isolated part that we had before, this root of trust that is isolated from the host. And the hardware encryption is a property of such a confidential computing trusted execution environment. And the VMs that are started on this host, they are isolated by the host. Like there's a firmware call to create a virtual machine, and the host is not able to kind of inject itself into this. So examples for this technology are the AMD SNP, Intel TDX technologies for x86 architectures. For ARM, there's CCA, and even for IBM, they have secure execution, I think is the term. So this is like a technology that many CPU vendors have. And also NVIDIA, for example, on their latest H100 GPU, they have confidential GPUs. And like the process is not that much different from what we had before. It's just that the CVM, when we launch it, is started with a kind of safe state that is measured. So registers and RAM and other CPU state is delivered to this call to start a guest VM, a confidential guest VM, and then we get a launch measurement from the secure processor that is essentially like a single hash. And the guest can request then, like we saw with the quote before, an attestation report from the hardware. That is, again, the evidence that is signed by a sealed key. Yeah. And I think the only differentiation here is, like, we have measurements in there. We have maybe also hardware effects like firmware revision, microcode, etc., and which encryption features have been activated. But the rest is more or less like with TPMs and other non-confidential integrity systems. So we just have basically the fact that TE is running encrypted as an additional fact, almost like the software. Okay, so then we have covered integrity, we have covered trust, attestation as concepts. We have then established that confidentiality is more or less a combination of hardware technology and those concepts. And containers we already know, so confidential containers should be fairly trivial. And this is not the case because there's just two different paradigms. Like a very simplified privilege model for Kubernetes we look here is essentially the users are have very little privilege, while the infra operators, the people who work in the data center, they have a lot of privileges. And the rationale behind this is we have to protect the infra from malicious users. We have the from users, from siblings, those kind of attacks. The trust model for confidential containers is exactly the opposite. Like we trust the users of an application a lot more than the cloud provider we deploy it on. So we essentially need to deprivilege the operators to not be able to look into a container workload. And this is not trivial because in Kubernetes, those concepts are in code, essentially. Like this is hierarchy. So the confidential containers project, there's multiple options to do confidential computing with containers and Kubernetes. The confidential containers CNCF project settled on confidential pods. It's very nice because pods are like a unit of computing in Kubernetes that is just not like one container, maybe multiple containers, but it's one way where we can conceptually hook into, and it's also very nice because you can run it on a managed Kubernetes offering, for example, and have pods that are confidential running alongside unencrypted pods, so you don't need to go all in. You can mix and match And the prior art is already there. Yeah? So confidential computing is mainly a VM technology. And we have Kata containers as a project that already achieved this to start pods in VMs to isolate them. Yeah, and I'm speeding up a bit, but there's problems here when we want to reconcile paradigms. Yeah, so we cannot trust the node in confidential containers. We need to verify that the pod spec the guest receives is actually what the user intended. So we need to kind of also make a measurement of this, of the OCI spec, essentially. We need to basically reject all host-injected resources, like everything that's untrusted, we have to reject. That's environment variables, that's storage, config maps, image layers even, and runtime APIs are problematic as well. So if you just can exec into, if an admin can exec into a confidential container, that's kind of undermines its purpose. And there's dynamisms in pod specs that we have to cover, so I don't go into detail, but it's very tricky. You see, like every service receives like a different set of envs. Yeah? You cannot write like a measurement, a static measurement for all of those. You have to cover this. And the solution is essentially you write policies that try to express those dynamic aspects. And here, that would be the demo. If my box would work. But yeah, what the demo would show is essentially how secure key release works in practice. It's essentially just a curl call to an like internal helper tool that will perform this remote attestation and get a secret key. So I think I will link to the AskKinema recording in the slides later. I just put a link to the last slide where I put the links. And to sum up, I think the takeaways would be that cloud native is an attractive platform for confidential computing, that we want to understand trust, integrity, and remote attestation as concepts if we want to leverage confidential computing, and also that things are still hairy. Like confidential containers have really specific non-trivial challenges that are also exciting because it's like a way for people to collaborate or get involved. So if you want to write, Rust code, this is something that the project I think has a lot of potential for newbies to go in and like contribute to APIs and just a lot of tooling that needs to be written to make things easier. So you don't need to be like a crypto expert in this kind of field. There's a lot of options. And that would be it from my side. Thanks a lot for listening. And yeah, open for questions.
Thank you very much. We're a little bit out of time, but maybe we have time for 1 or 2 questions. Yes.
From a pipeline perspective, so at some point, this metadata I use to deploy my pod and the image and all the stuff which has to be signed needs to be signed in this development pipeline, right? So I would have to have some kind of new package which have all this information along with the normal deployment, and this all goes then in the cluster and down to the hardware, evaluated and back.
How it works, like there's different ways to do this. I think the most simple one is to say you have like a golden measurement of your like an abstract deployment, and this you put into your remote verifier. Yeah? So the remote verifier has a list of values, and then it gets the evidence. It checks whether the signatures are correct. It actually, checks whether the AMD root key has actually, is the source of the signature that has signed the evidence, you verify this, and then you can look at the values that you received. And this is basically what you can choose. And a gold measurement means like you just put the value that you expect to be in there.
Okay.
Okay. Thank you for the questions. We are really running out of time. Please catch Magnus on the hallway if you have further questions. Thank you.